50 pounds for that instant, enough force to shear lead and crush steel. Conventional design techniques were useless. Something entirely new had to be invented. In the autumn of 1940, the problem went out to industry. Western Electric and the Radio Corporation of America were pressed into service to shrink and stiffen tubes. Specialty glassmakers began formulating stronger envelopes. Smaller firms experimented with planar electrode geometries to spread load and prevent internal collapse. Engineers discovered that routine assembly, soldered leads, loose internal supports, epoxies that cracked, meant immediate failure under acceleration. The solutions were inventive and painstaking. Glass chemistry altered with additives to reduce brittleness without compromising vacuum integrity. Internal components potted in shock-absorbing compounds. Electrodes reworked and spot-welded to create mechanical bonds that would not shear. Tiny supports brazed into place to prevent flex. It was a war of tiny tolerances. By spring of 1941, after thousands of prototypes and 1,000 small catastrophes, production lines began to turn out tubes less than an inch high that could survive the mind-bending forces of firing. Power was another masterpiece of practical engineering. Traditional batteries were useless. They would either leak, short, or remain inert. The solution, conceived and perfected by researchers at the National Bureau of Standards, was brilliantly simple and elegant. A battery that only came to life when the shell spun. A glass tube, charged with electrolyte and sealed between metal plates, stayed dormant at rest, the liquid isolated from the contacts. The moment the shell left the barrel and spun at hundreds of revolutions per second, centrifugal force drove the electrolyte outward, forcing it against metallic contacts embedded in the tube walls. A chemical reaction produced current only while the shell spun, which both powered the fuse and served as an intrinsic safety. A fuse without spin could not accidentally fire in storage or during handling. It was the kind of clever, low-tech fail-safe that saved lives in the workshops as much as on the deck plates. Proof of concept moved from bench to range. On May 6, 1941, at Dahlgren Naval Proving Ground, a small fleet of prototype fuses, 6 units from the NBS team, were loaded into aerial bombs and dropped over water. The transmitters sang, receivers picked up reflections from the sea, circuits closed, detonators fired. All 6 exploded at their designed altitudes. It was a crucial milestone. The electronics worked in a falling bomb. But bombs, released from aircraft, experienced only hundreds of Gs on launch. Artillery presented a challenge 2 orders of magnitude tougher. To test the true limits required creative abuse. Shells were fired at instrumented ranges. They were catapulted in giant centrifuges that simulated barrel accelerations. They were shot into steel plates and sky blue targets to measure survivability. Early artillery tests produced a litany of failure modes: tubes that pulsed for an instant then died, solder joints that vaporized under stress, circuit traces that cracked from inertia. But each failure yielded a fix. Better filaments, reinforced welds, revised geometries, potting compounds that cushioned without dampening radio performance. Manufacturers retooled factories, machinists learned new tolerances, and production engineers wrote the manuals for a technology no one had imagined a year earlier. Secrecy threaded through every decision. The program's name, Variable Time, was deliberately opaque. Production was compartmentalized. Many hands on the line knew their work only as an anonymous part of Section T. Drawings were stamped with code numbers. Shipments were split between yards and routed through fake manifests to conceal their destination. The military feared 2 things: that a single captured document could let the enemy copy the invention, and that premature disclosure would trigger countermeasures. That caution paid off. The enemy did not know what hit them. When the first hardened fuses were finally shipped to combat zones, they were used cautiously and sparingly, held in reserve for critical battles. Sailors tested their mettle in practice and kept a wary eye on the new tubes, half expecting some catastrophic malfunction. Then, on that January night in 1943, everything changed. The shell that detonated 30 feet from a Japanese VAL and turned it into fire and scrap was not an accident. It was the result of 2 years of frantic engineering, the distilled product of graphite plans, sleepless machinists, experimental glassworks, and the peculiar genius of men who could imagine circuits that would live through the worst shaking a human mind could conceive. Once the fuse proved itself in combat, the tactical consequences were immediate and far-reaching. Anti-aircraft fire lost its old randomness. Where once gunners had fired curtains of lead, hoping some fragments would cross a plane's path, now a single shell detonating near a wing showered it with lethal fragments. The number of shells required to cripple or destroy an aircraft plummeted. Formations that had once dared to mass in the hope of overwhelming defenses were now haunched by the knowledge that a near miss could be as deadly as a direct hit. Pilots described the new threat in tones that mixed awe and dread. Planes vaporized by unseen hands, whole squadrons broken by invisible bursts that seemed to detonate for no reason they could see. Kamikaze tactics, built on the grim certainty that the plane would at least strike its target, lost much of their finality as fuses shredded aircraft before they reached the decks. The proximity fuse also reshaped campaigns. In the Solomons and the Central Pacific, it blunted air attacks and reduced losses among escorts and transports. At Okinawa, where kamikaze swarms inflicted terrible damage, VT-fused shells were one of the few defenses that could reliably break the massed incoming waves. In the Atlantic and over Britain, proximity fuses raised the kill rates against V-1 buzz bombs and made air defense of cities and harbors far more effective. In quiet moments after engagements, sailors would look up at the night sky streaked with tracers and imagine the tiny iron theater of war inside each shell nose, the squat, humming tubes, the potting compound like hardened honey, the spin-activated battery alive for an instant to save a life. By war's end, Section T's invention had earned a place alongside radar and the atom in the catalogue of transformative technologies. It had not ended the war by itself, but it had altered countless battles and triumphed where arithmetic had once doomed defenders. And yet its greatest lesson was not only technical brilliance, it was how a small problem, how to detonate a shell near its target, became the fulcrum for vast industrial creativity. From the chemistry of glass to the geometry of welded electrodes, from centrifugal batteries to secret production lines, the proximity fuse was a story of practical imagination, meeting desperate need, and of how tiny things can tip the balance of great conflicts. By June 1941, Section T had grown from a handful of dreamers into a feverish engine of more than 100 engineers, physicists, and ordnance specialists. A former automobile dealership in Silver Spring, Maryland, became the main laboratory. Blackout curtains muffled light and sound, guards patrolled the lot, and neighbors whispered about odd deliveries and men who never spoke of their work. The cover story, Optical Instruments, was bland on purpose. The true mission was uglier and more urgent. A crash program to build a device Allied commanders believed could change the course of the war. The list of technical hurdles read like a nightmare drawn up on a drafting table. The antenna had to be compact yet efficient. Engineers finally settled on a ring antenna that hugged the fuse body, an elegant compromise between size and performance. The transmitter needed to sing at frequencies, roughly 70 to 90 MHz, that produced a useful Doppler return without demanding impossibly large coils or capacitors. Designers squeezed transmitter functions into no more than 3 miniature vacuum tubes. Receivers had to pluck a reflected whisper 1,000,000 times weaker than the transmitted signal out of the static, so amplifier stages using 4 tubes were stacked to create the necessary gain. A Doppler discriminator compared the outgoing and incoming frequencies and closed an electrical contact when the difference crossed a preset threshold, the moment of lethal proximity. All told, each fuse contained roughly 130 miniaturized parts that had to work together after months in storage during the shock of launch and while the nose of the shell spun like a top. Pearl Harbor burned through the veil of doubt. Before December 1941, some naval officers still believed electronics would be pulverized by gun launch. After Pearl Harbor, the calculus changed. Time fuses had already demonstrated their deadly unreliability, dropping shells into Honolulu had taught a bitter lesson, and the Navy moved urgency to priority. Contracts ballooned from millions to hundreds of millions of dollars. Johns Hopkins. Applied Physics Laboratory was founded on March 10, 1942, to centralize development, translate laboratory drawings into production blueprints, and shepherd the program from prototype to factory. 5 companies, Crossley Corporation in Cincinnati, RCA, Eastman Kodak, General Electric, and McQuay Norris, signed on first, committing factories, tooling, and manpower. The industrial web grew quickly. Over 100 factories would ultimately supply sub-assemblies for fuses that each contained that bewildering lattice of 130 parts. The production target was audacious: 40,000 fuses per day by late 1943, 70,000 per day by war's end, numbers that demanded entire plants be reorganized and entire new workforces trained. Secrecy was woven into the project's DNA. Workers on an assembly line might solder a sub-assembly for years and never know what the finished product would do. Subcontracts were split, so no one plant held a complete blueprint. Variable time, VT, was a deliberately misleading designation. In military correspondence, the code word PZT slipped between lines to hide intent. Even when tests began and broken fuses washed ashore, enemy intelligence, German or Japanese, never unraveled the truth. To the adversary, it was simply a mysterious new time fuse that misfired or failed. To the Allies, it was a guarded miracle. Proof came at sea. On August 12, 1942, in Chesapeake Bay, the cruiser USS Cleveland staged the first comprehensive test of production fuses against radio-controlled drone aircraft. 3 drones were launched. The ship's 5-inch batteries needed fewer than 10 rounds to destroy all 3 on that first day. The remaining days of the scheduled 2-day trial were cancelled, and admirals ordered immediate mass production and deployment. The numbers were staggering next to 2 years of old performance, where time-fused shells had required, on average, 2,500 rounds per aircraft destroyed. Proximity-fused shells cut that requirement by roughly 25 times. The arithmetic was suddenly merciful. Production rolled through the autumn of 1942, and the first combat-ready fuses reached fleet units in October. They arrived under strict conditions. The cruiser Helena was issued 500 rounds of VT-fused 5-inch ammunition, parcels so carefully parceled that orders forbade their use except over water. Any dude would sink and be unrecoverable by the enemy. Crews were drilled on handling and firing, but were told nothing of the bright mines and fragile tubes tucked into each steel nose. Curiosity mixed with a healthy dose of military caution. Initial reactions ranged from cynical skepticism to guarded curiosity, which is to say, most sailors treated them like another piece of unproven kit until the night that proved otherwise. On the decks of Helena in January 1943, those first issued fuses found their purpose. The sequence of a single engagement that night changed naval air defense forever. Where previously men had fired strip curtains of shells and prayed that something would intersect a plane's path, now a relatively modest barrage could produce devastating results. One Japanese Val, a dive bomber trained to survive an ocean of flak, flew into the zone of a detonating VT shell and evaporated in a sheet of flame and ragged metal. No one aboard saw a direct hit. What they saw was the sudden absence of an aircraft that moments before had been whole and turning away. Stories moved fast. Pilots later told of invisible bursts that shredded wings, flight controls flayed by fragments from shells that had never needed a clock to explode. For the Japanese, whose doctrine often counted on reaching the ship with a last-ditch strike, the fuse robbed them of certainty. For American sailors, the fuse bought seconds, enough seconds over thousands of engagements to save lives. Tactically, the consequences were immediate. Attack formations tightened and then loosened. Pilots hesitated where they once pressed on. The kamikaze, whose grim calculus relied on at least one contact strike, found that many of their final dives were interrupted by explosions that tore the aircraft apart before they could make contact. Ships that had trained for muttered dread at the sight of incoming planes now could point to a new confidence. With VT fuses in the magazines, their escorts and transports were less likely to be shredded by massed raids. At Okinawa, where kamikaze waves reached apocalyptic density, proximity-fused shells were among the few weapons that could reliably blunt the onrush. The fuse's influence spread beyond fleet decks. British anti-aircraft batteries embraced VT rounds to defend cities from V-1 buzz bombs and to thin bomber streams. The statistical advantage was plain and pragmatic. Fewer shells, fewer sorties, fewer sailors and civilians killed. By the time production had ramped and the fuses were in widespread use, the device had moved from guarded secret to indispensable tool, though the secret of exactly how it worked stayed compartmentalized long after the sound of guns had faded. In the end, the proximity fuse was more than an item on a wartime shopping list. It was a thesis about modern warfare that a math problem, how to detonate within yards of a target moving at hundreds of miles an hour, could be transformed into a practical instrument by patient, granular engineering. From a repurposed car lot in Maryland to the assembly lines of Cincinnati and Rochester, from the lab benches of Johns Hopkins to the decks of the Pacific Fleet, hundreds of thousands of hands produced something that changed the calculus of battle. Men who never read the blacked-out memos, who merely tightened bolts or tested jars of glass, had contributed to an invisible guardian that, for the rest of the war, made the air a less certain place for the enemy and a little safer for those below. The morning of January 5, 1943, resolved every lingering doubt. Lieutenant Red Cochran's salvos from USS Helena did what decades of gunnery theory had failed to achieve. One Japanese Val dive bomber was torn from the sky, another was ripped open and forced from its run. The gunners had killed aircraft without perfect prediction, without time-consuming manual fuse setting, without the laborious calculations that had defined and limited anti-aircraft fire since the very beginning. Word swept through the fleet almost immediately. Crews who had once muttered skeptically about magic shells now clamored to use them. Ships that had received allocations of the new proximity fuses began deploying them in every engagement. Reports filtered back up the chain of command. Cruisers, destroyers, even the great battleships were claiming kill ratios far beyond anything achieved with conventional timed fuses. Enemy aviators noticed it too. Something had changed, though they could not grasp what. American flak was no longer just a wall of steel, wasteful, imprecise, survivable if one had the nerve. Now, aircraft seemed to be plucked from the air by unseen hands. By March 1943, a mere 3 months after Cochran's historic salvo, proximity fuses made up only 25% of the Pacific Fleet's anti-aircraft ammunition, but accounted for over half of all Japanese aircraft destroyed by naval gunfire. The numbers told their own story. VT-fused shells proved 3 times more effective than time-fused shells under daylight conditions, and in night actions where visual tracking was nearly impossible, their advantage grew to 7-fold. What had once required massive barrages of fire could now be accomplished with a fraction of the expenditure. Efficiency became lethality. Ships that once relied on walls of steel suddenly possessed precision that seemed uncanny. The Japanese, for their part, adapted, but without success. Allied intelligence tracked the tactical shifts with interest. Enemy bombers began flying higher, sacrificing accuracy in the hope of staying beyond effective range. Torpedo planes skimmed the wavetops, hoping to confuse Doppler circuits with reflections from the sea surface. Dive bombers steepened their attack angles to shorten the window of exposure. But each adaptation carried a cost. Bombs missed more often, torpedoes splashed uselessly, and steep dives led to pilot error. Accuracy collapsed, while losses mounted. The shift was strategic as much as tactical. Admiral William Bull Halsey himself credited proximity fuses with fundamentally altering the balance of power at sea. Japanese torpedo bombers, once among the most feared threats, had relied heavily on night attacks where defenders struggled to see and timed fuses were useless. Now, radar detection guided gunners and VT shells made every round dangerous, even in total darkness. By the end of 1943, the paradox was striking. Only a quarter of the shells fired carried proximity fuses, but they accounted for the majority of aircraft destroyed. Yet the most dramatic test still lay ahead. October 1944. The Philippines. The Japanese faced inevitable defeat, but desperation can breed terrible invention. Out of that desperation came the Shinpu Tokubetsu Kogekitai, the Divine Wind Special Attack Units. The world would remember them by another name, the Kamikaze. The tactic was simple and terrifying. With experienced pilots already lost to years of attrition, replacements were barely trained. Precision bombing and torpedo runs were impossible, but anyone could fly straight. All that was required was to aim an aircraft, often packed with explosives, at an American ship and ride it down to impact. No escape, no survival. It was a weaponized suicide, born of desperation and fatalism. Against such a threat, proximity fuses were essential, but they also faced their greatest limitation. In conventional attacks, aircraft approached, dropped their payload, and tried to escape. Destroying or even damaging the attacker often meant the ship was safe. With kamikazes, there was no escape phase. Pilots kept driving their machines forward even as wings shredded, engines burned, and cockpits filled with smoke. Aircraft that would have aborted in conventional attacks now continued, sometimes surviving long enough to crash into their targets even after sustaining mortal damage. The answer was brutal concentration. American ships increased rates of fire, layered their barrages, and fired earlier at longer ranges. Instead of relying on damage to discourage attackers, gunners sought total destruction in the air. Proximity fuses multiplied their chances, detonating near attackers and blasting them apart before they reached lethal range. On May 11, 1945, radar picket duty off Okinawa offered a stark illustration. The destroyer USS Hadley and the destroyer escort USS Evans found themselves facing 156 Japanese aircraft in a 90-minute onslaught. The two ships fought like cornered animals. Hadley alone shot down 12 attackers before 4 kamikazes, already mortally wounded, still managed to smash into her hull. Evans claimed 23 kills before she was forced to withdraw, damaged but afloat. Post-action analysis showed the stark truth. Without proximity, fuses detonating shells at ranges where time fuses would have been useless. Both ships would almost certainly have been overwhelmed and sunk within the first half hour. Instead, they survived long enough for support to arrive. The numbers are merciless and conclusive. Between October 1944 and August 1945, U.S. naval forces destroyed 278 Japanese aircraft using VT-fused ammunition. Analysts later calculated that, under the same conditions, only 46 would have been destroyed with conventional fuses. The ratio was 6-1. Every one of those extra kills represented a ship saved from fire and steel, sailors spared from drowning or burning, and convoys that could continue steaming toward the Japanese home islands. By war's end, the proximity fuse stood tall beside radar and the atomic bomb as one of the 3 decisive technologies of the conflict. It had not ended the war in an instant like the bomb, nor given eyes over the horizon like radar, but day after day, battle after battle, it had shifted the arithmetic of survival. Where once 2,500 shells were needed for a single kill, now a dozen might suffice. Where once bombers dove with impunity, now they dove into a curtain of invisible death. It was, in the words of one admiral, the little gadget that won the war.